Say we have a function f and it has its first n derivatives available at a real number c. That is to say, these first n derivatives, they exist, and let's just review the notations. That is, this superscript 1 indicates that this is the first derivative, the superscript 2 indicates that this is the second derivative, and the superscript n indicates that this is the nth derivative. So under these conditions, we define that the Taylor polynomial Pnx of degree n of the function f is given by this equation. And in the case when this point, the value of this point c is 0, we call the Taylor polynomial Maclaurin polynomial. Let us look at an example. So before I do an example, let's erase this part of our slate. Okay, and so what we are doing is this, that we are calculating Taylor polynomial, or actually in this case we are going to look at Maclaurin polynomial of the function e to the x. Okay, and e to the x, you know, it's a function that's fairly easy to differentiate because the derivatives of all orders of e to the x are what? E to the x itself. And since we are going to need the values of the derivative at the point c equals 0, so we will note that all the derivatives at 0, each of them equals how much? They all equal 1, and of course the value of the function at c is also 1. So if we substitute all these values in this polynomial, what we will get as the Maclaurin polynomial or Taylor's polynomial centered at 0 for e to the x is this polynomial of degree n. So let's see that how do these polynomials, they relate to the function. So the function that we considered, e to the x, and let me just clean the slate to get some space here. So what we just obtained is, or are, that the Maclaurin's polynomial of degree n is this, and if we look at degree 0, degree 1, 2, 3, 4, say up to 5 in this case, then the polynomials can be described in this manner. Now let's look at this whole phenomena graphically. So let's look at a graph of e to the x, a familiar graph for all of you, and then say we go ahead and add the Maclaurin polynomial of degree 0 in this window. What would we get? We would get a straight line, y equals 1, and of course it meets the graph of e to the x only at one point, and I didn't have much expectation from this anyways. Now if we go ahead and graph the polynomial of degree 1, that is the linear function, you can see that that's going close together with this a little better. And now let's successively graph the polynomials of higher degrees. So here is that of degree 2. Okay, then we will go for degree 3. So here is degree 3. You can see as I'm increasing the degree of the polynomial, the approximation is getting better. So we had 3, then we had 4, okay, or rather we have 4. So 4 goes along this far, and so let's just do to the point or to the place in this window that we get at least a good approximation on this side. So I'm placing a polynomial of degree 5, we have right here. Now let me go for degree 6, and for degree 6 we get this close. Now let's go for degree 7. Okay, and for degree 7 we have got an even closer, and then let's go for degree 8, and we are yet closer, and then I think degree 9 should do that here in this window. And you can see that we are looking at Maclaurin, which is approximation at 0. So we have to go farther and farther to approximate this e to the x in this window, and we have stopped at 5. So we will see later it might be better to look at the polynomials at c equals 4, and then we may get an approximation in this region with polynomials of lower degree. So here we have 9th degree, and let me not just take your time and just doing this forever.